Hi, welcome to the next lecture on section 3.6. We will be talking about functions, and to understand a function first, we have to understand what a relation is. Now, if we're looking at relations, we're simply talking about a grouping of points, a set of values, if you will. So we're going to show a couple sets of values here. We have 9, -5 as our first point. 9, +5 as our next point, and 2, 4 as our last point. Now, within any relation that you have as a set of data like this, what you can do is determine a couple things that we call domain and range. Now, domain is simply talking about x values. That's all it's looking at. As you're looking at your range, it's talking about y values. Now, here's what this means for us. If I were to look at all of my values here, I have my x values and my y values. My domain would be listed from least to greatest, and it would be the set from 2 and 9. That is my domain. My range, same thing. You're looking at least to greatest, but now you're looking at the y values. So I have a -5, a 5, and a 4. So I have -5, 4, and 5. Now you might be looking at this and saying, wait a minute, it seems like you missed a number because my domain only has 2 numbers listed, but my range has 3 numbers listed, and my relation had 3 points. Anytime a value repeats in a relation, we do not repeat it in either the domain or the range. So if you're looking at something like 9 here and 9 here, well, those are both 9 for an x, which means you represent it one time. Everything else, like a -5 and a 5 for the y's and a 4 for the y, those are all unique values. So you have to list the unique values. Let's try one more just to get an understanding of what it is we're looking at. So my next relation has a point of 6, 3, 4, 3, and -2, 1. So the question is, what are my domain and range? Well, my domain, again, I'm looking at the x values here. So I have 6, 4, and -2. So it's a -2, 4, and 6. My range, I have 3, 3, and 1. So I have 1 and 3. And that would be my domain and range sets. Now, whenever you're looking at the idea of a function is based on a relation of data, but the x values of a function cannot repeat. So I'll say that one more time. A function is based on a relation, meaning a set of data, and the x values cannot repeat to be a function. Now, this is actually pretty easy. As we're looking at this two sets of data, our two relations, let's determine whether or not we have a function. In this instance, the first set of data that we have, the first relation, my 9 repeated. So that means I had an x that repeated. This is not a function. Let's talk about the second relation. I see that my 3 repeats, but those are y values. Those are okay to repeat. None of my x values repeated. They're all unique, which means this is a function. So when we're looking at our data, it's very important to really analyze our domain and our range. That domain, again, cannot repeat if you're planning to have a function or if you're analyzing to see if you have a function. This is not a function because one of your domain values did repeat. This is a function because all of your domain values were unique. Now, that being said, there is a very special way that we do function writing. And what we're looking at is something called function notation. Function notation looks really scary, but it's really easy. So it says f of x, and this is technically equal to y. Now, what does that actually mean for us? As you're looking at this particular problem, you have an input value and an output value. Hey, look at that. It's x and y. It's almost like an XY chart where you have an input value and an output value. Go figure. Now, what is f? That's the big question, right? What is f? Who said it had to be f? Why can't it be h? Why can't it be g? Why can't it be Bob? Bob the function. That's what I like. Now, all that is simply saying is the name of the function. So this little indicator, whatever it happens to be, typically F, G, and H are used a lot. That is simply the name of the function. So that way, if we're working with multiple functions, we don't get them confused with one another. We can easily distinguish between different workings. Now, that being said, function notation is super easy to use. So let's play with one. Here's our original function. So we have f of x is equal to 2x squared minus x plus 3. Now, if we were to say solve for f of 0, what we're saying is that we are going to input 0 everywhere that we see a x variable, because x was our original variable. So what we're going to do is plug in. I like to use parentheses just to show where those variables are. And it also helps to use the parentheses so that you don't lose your sign. So this is what I've got. I'm going to go ahead and simplify this. 0 squared, 0. 2 times 0, 0. Minus 0, still 0. Plus 3 is 3. So I get, by plugging in 0, I get 3 as an output value. So that means my function at 0 is 3. Okay. What if I had my function being evaluated for -7? Okay, let's try it. So I have 2 times -7 squared minus a -7 plus 3. Now you might see why I use those parentheses very clearly here, so I don't lose that sign. So -7 squared is 49, so that's 2 times 49. This is plus 7 plus 3. 2 times 49 is what? 98 plus 10. You get 108 for when the equation has an input of -7. So your function at -7 is 108. Interesting. Let's try another one. Let's say that function, same function, f, I haven't changed yet, is being evaluated at 3. So what we're going to do is we're going to simply plug in. Three squared is 9. -3 plus 3 is 0. That cancels out. 2 times 9 is 18. So my function at 3 is 18. Now, this is really, really helpful as you're working through problems on a page or as you're doing multiple problems together. So the function notation really helps to identify input and output very precisely. And again, it's kind of like that XY chart. You're just doing it in line as opposed to charting that data. Now, if you were to look at your values for points, this would give you a point of 0, 3. This would give you a point of -7, 108. And this would give you a point of 3, 18. So function notation and coordinate graphing really go hand in hand here. Now, how do you know if you're looking at a graph whether or not you're looking at a function? So think about our discussion just a few moments ago. We said that you can't have a repeating domain value. Remember, domain is your x. So you can't have a repeating x value in your graph either. So if I'm looking at a couple examples, there's 4 examples at the bottom of your page. I'm going to put those up right here as best I can. Again, I am not to scale with my drawings here, but I don't need to be to get the point across. Now, these are 4 different graphs, and we want to find out whether or not these are functions. What we do is something called the vertical line test. The vertical line test is super easy. We take some kind of ruler, pencil, whatever it happens to be, nice and straight, and we can take it from left to right across the graph. As we move across the graph, you should not encounter more than one x value at any given point. If you do, then you are not a function. So in this case, no, you do not. You do not cross any additional, you do not cross any duplicate x values. So yes, this is a function. How about a circle? Well, just to show emphasis, there's the same x value twice. And you can see that throughout the circle, you'll have multiple repeating x values. So this is not a function. What about a line? Moving left to right. Yep, that looks like a function to me. What about this squiggly looking line? As you move left to right, yes, it is a function because there are no repeating x values. So as you're looking through trying to determine whether or not a graph is a function, you can use that vertical line test. And it's very effective, very quick, and very easy to use. Now, let's do a little bit more with understanding about functions, especially the understanding of domain. Because domain really helps to expand our understanding of what are the boundaries for an equation, for a function. And you can think of this kind of like a building. If you think of a building, you're on the top floor of that building, there's only so much you can walk on in that same plane of existence, right? So if you were to walk outside of the building and you're on the top floor, meaning you're stepping off the building, you are now outside of that domain of where the floor is. You fall off, of course. Don't do that. Disclaimer, don't jump off buildings. Okay, that being said, we're looking at how far can you really walk? What is that domain value? How is it represented? So if you were to look at some prime examples here, let's say I have y is equal to 1 over x minus 2. Now, I know we haven't really gotten to these types of equations just yet, but you don't really need to understand how these are graphed to understand the concept of domain. Instead, think of it like this. Can you divide by 0? No, you can't divide by 0. So what can we do? At this stage, I see that x is in the denominator. X, being a variable, can change. So we need to find out what this cannot change to, because we cannot divide by 0. So let's try that. So I know I cannot divide by 0. So I'm going to set my x minus 2 so that it cannot, it's an equal sign with the bar through it, cannot equal 0. Solve it just like a regular equation. X cannot be 2. What does that mean? What happens if I plug 2 in here? You get 1 over 2 minus 2. 2 minus 2 is 0. You get 1 over 0. You're dividing by 0. Can't do that. So x cannot be 2. Can x be anything else? Yes, it just can't be 2. So we represent this in interval notation, and you've already had practice with interval notation. So interval notation is saying that if you think of it visually for a moment, here is your 2. X cannot be 2, right? X can be anything up to 2, and x can be anything after 2. X just cannot be 2. You may also see this represented with an open circle. Same exact idea. So that being said, I know my interval notation goes from a negative infinity up to 2. I'm using a parenthesis because I cannot include 2. Remember, a square bracket means you can include that value, but a parenthesis means you cannot include that value. Since I cannot equal 2, I cannot include it. So this explains this part right here. But what about this part? What about that part being 2 to infinity and beyond, as Buzz Lightyear would say? Well, that part is also true, which means we have to union these or marry them together. And so our interval notation is actually showing us a gap at 2. So it's from negative infinity to infinity, but there's a gap at 2. We cannot include 2 as a value. Okay, very simple, very easy. Let's try another one. Let's say I have y is equal to 5 over 2x plus 7. Let's see what happens in this situation. So I know I can't divide by 0, so anytime you see an x in the denominator, you need to find the domain, and that is going to be set easily by setting the denominator so that it cannot equal 0. Okay, let's solve. Subtract 7, divide by 2. X cannot be 7 halves. What can x be? Anything else. How do we represent that? It goes from negative infinity to a negative 7 halves, not including, union a negative 7 halves to infinity. You have to have that union because you have both sides. If you were to physically graph it like we did previously, you could see that you have both sides and you have to represent both sets of true data. Okay. Now, that being said, linear equations will have an unrestricted domain with the exception of one line, a vertical line. And so if you're looking at any equation such as y equals x plus 2, this would simply be something like this. There are no gaps. It goes on forever and ever, either direction. And so your domain here would be from negative infinity to infinity. Very easy, very straightforward. There's nothing that can falsify this because the x is not in a denominator and it's not under a radical sign. If you happen to see x in a radical sign, you start to run into an issue there. The same thing goes for parabolas, which we haven't talked about just yet, but you can see an example of that on your notes. And you saw a visual example just a few minutes ago. So something like this, where x is squared, you have y equals basically ax squared plus bx plus 0. There's nothing out here, but that would be standard form of a parabola. This is going to show you a representation very similar to something like that. The domain here is also unrestricted. You can use anything from negative infinity to positive infinity. And the same thing goes for absolute value. If you were to look at that last example that they have listed here in the notes section, I can plug anything into this absolute value and it's still going to be true because x cannot be changed where it is false. Okay, that being said, let's try looking at a couple examples. You have them scaled on your actual notes, so I suggest looking at that. However, for the purpose of discussion, I am going to draw as best I can here. I'm going to go ahead and just get all three of these up here, because I also want to talk about range for a moment. That's a circle, go with it. And okay, perfect. So looking at my three visual examples, my three graphs, I need to determine the domain and the range. So domain visually is pretty easy. Look as far left and as far right as x can go, and look to see if there are any gaps that are noticeable. In this case, x starts right there. There's nothing on this side of -1. So that means my domain goes from a -1 to infinity. It just keeps going this way. The question is, do I include that -1? Yes. As you look at your graph, you can see that -1 actually has a solid dot to it. And I tried to represent that here as best I could as well. But that would mean that you use a square bracket. The domain here is from -1, including -1, to infinity. Let's talk about the range. The range for this top graph right here. I'm going to separate those a little bit. The range is talking about the lowest possible y value to the highest possible y value, also looking for any gaps. Now, it's a little hard to see, but this is slowly increasing, very, very slowly increasing as it continues onwards. But the lowest possible y value is 0, because you're here at the axis, right? So here's your axis, you're here, that means you have 0 as your lowest possible y point. Your highest would be infinity, and I have no idea what I was just drawing there. But that's an infinity symbol. There you go. Now, can you include 0? Yes, you're sitting on the axis, you have a solid point. So that means you're including 0 to infinity for the range. Let's talk about this circle. Circles are fun. As we're looking at this particular circle, we want to identify again domain and range. I tried to draw this to scale, so I suggest using your diagram that's already provided. But as you're looking at this scale, notice that my circle passes through 2 units in either direction, and it is a circle. So my domain is talking about my x's. My lowest x is a -2. My highest x is a +2. I am definitely passing through those points, so they are included. Let's talk about the range. Lowest point is -2. Highest point is -2. That means I have a -2 to 2, and I am also passing through those points. So in this case, my domain and range are the same. Let's look at this last example. The domain, we're looking from -infinity to +infinity. Notice these arrows, they keep going. That means x keeps stretching as well. So that domain is going to be negative infinity to positive infinity, but my range starts here at 0. So I'm sitting on the axis, and I'm going vertically up. So I'm going from 0, including it, to a positive infinity, if I can draw that. There you go. All right. Okay, so domain range, very, very important, especially for understanding the graphical sense of what an equation looks like, and also what can be excluded from that solution set. That being said, this concludes section 3.6 for us. I will continue with another section momentarily, or as soon as you click play.